Okay, good.
So I'm going to write down a homework problem for next week. And the second thing I'm going to do is I'm going to list all the steps for the small oscillations formalism. And maybe we'll even leave them on this side of the board and then we'll work on the other stuff. Okay. So the homework problem for next week is to very carefully construct the Lagrangian for the double pendulum. This is the kind of thing you can find all over the place because it's so classic. But the idea here is that we have two connected ideal pendula. So that's phi1, L1, M1, and then phi2, L2, M2. So that's a double pendulum. And the first thing we want to do is construct the Lagrangian. And I'm going to start this one off. Construct L equals T minus U. So we need the kinetic energy. But what we have here is in a different color. The coordinates, and they're there are x1, y1, and down here we have x2, y2. Right? And they're not independent, so we have to do a bit of work. So if we start with the kinetic energy, 1/2 m1 x1 dot squared x2 dot squared plus 1/2 m2. Sorry, this was y1 x2 dot squared plus y2 dot squared. But those are just the individual kinetic energies, half mv squared v1. And u is just going to be m1g y1 plus m2g y2. So those may be kinetic and potential energies, but these coordinates are not independent. So we can't use that for a Lagrangian yet. So the second step, actually this is going to fill the board, that's where it goes. The second step is that we have to say, okay, x1 is equal to L1 sine phi1. Y1 is equal to minus L1 cos phi1. That'll do the trick. X2 is equal to x1 plus L2 sine of phi2. And y sub 2 is equal to y sub 1 minus L2 cos phi2. And so we can actually go into here and say L1 sine phi1 plus L2 sine phi2. And you can fill in the other ones as well. So now it gets fun. I'll just do these two here. X1 dot is equal to L1 cos phi1 phi1 dot. And x2 dot is equal to L1 cos phi1 phi1 dot, which is what we have right there, plus L2 cos phi2 dot. So you have to systematically go through these things, square them and sum them, and it's going to be pretty complicated looking. But be aware, this is still the simplest form of this problem. That's the way it goes. Okay. So anyway, you do all of this now. Now when you have all of these, y1, y2, everything, and now you construct L equals T minus U, what you obtain is, so what was that? I'll say 3. Now L is equal to L of P1, P2, P1 dot, P2 dot. So that's the form that we're looking for. And we want it to look like this. 1/2 something P1 dot squared. Just putting those blanks in there. P1 dot P2 dot P2 dot P1 dot. This is kind of a redundant thing, but it's a standard form. I'll put question marks here, right? And P2 dot squared. And that's the standard form. Then I'm just going to write minus U of, no square bracket there, minus U of P1 and P2. And these 4 mystery coefficients, they form that matrix. Okay. So these things give us that A I J of P1 and P2. And that'll be enough for starters. And what we're going to do next, so since I'm numbering these things 4, we're going to construct the small oscillations Lagrangian that we've been talking about. And the 5th step is going to be find determinant negative omega squared m plus k equals 0. The characteristic polynomial. Here I'll put here L small oscillations, the matrix Mij, the matrix Kij. So we're going to do this one really systematically, and then Sam or somebody else in this class will actually have the integration of the differential equation to see those results. So the full integration of the differential equation can't be done analytically, but it has really beautiful results. The analytical stuff that we're going to do is also important. It gives us the characteristic frequencies. So this is a whole project, and I'm just going to put a note here. This problem is actually related to this one that we did a while ago, where we have a mass and a pendulum hanging from it. This one's a little simpler than this one here, but we're going to come back to this one, we'll do this one, and we're going to have a nice set of problems under our belt, okay? So that's the program, and good, I'll leave that up there, and then we're going to cut to work it at the board.